Thank you very much for inviting me. I'm going to talk about what I thought was most appropriate given the notion of developing minds. The problem with this talk, it's one of the most difficult talks that I give. It's one of my favorites, but it's very difficult because it tries to cover lots of different levels of learning and inference, and as we'll see, structure learning. But I thought that would be particularly apt for this audience that wants to understand inference in the context of learning and learning in the context of selecting the right kinds of models in a developmental or a statistical sense. So I'm going to try and introduce active inference and the notion of self-evidencing, where self-evidencing just means trying to maximize the evidence for my models of the world, with a special focus on generative models and the fast kind of learning, namely inference about states of the world, specifically active inference, with then a focus on how we plan our behaviors in order to resolve uncertainty in that inference process and speak to notions of novelty and salience and epistemic affordance and how that emerges from a first principle account of behavior. And then finally, how all of this is contextualized in terms of optimizing the very structures of the generative models themselves and what kinds of processes would underwrite that structure learning. So in brief, we're going to be talking about inferring states of the world in the moment, and then at a slightly slower time scale, learning the model parameters, and then addressing the context in which that learning occurs, which is learning the model structure. To make this more engaging, I'm going to invite you to play a game. If you've seen this before, please feel free to cheat. It makes my job easier. The game is designed really to illustrate our remarkable capacity for discerning contingencies, structures, rules in our world. And I want to see how Bayes optimal you are in terms of this kind of structure learning. So I'm going to ask you to play the game, and we're going to do multiple trials, and then we're going to see how quickly it is before you get an insight until you discover the rule that underlies this particular game. And then I'm going to try and simulate an agent playing exactly the same game and under Bayes optimal principles, and see whether you are Bayes optimal in relation to the synthetic agent's performance. So here's the game. Jochen, I'm going to have to ask you, or no, I'll invite the audience to unmute if they can spot the rule. And if we can't, then I'll have to explain the rule to you. So this is a game. Your prior beliefs. You're going to choose the correct color based upon the arrangement of these three large circles. And what I'm going to do is give you the prior that the location of the correct color, the color that you should articulate, is designated or depends upon the color of the top or the center circle. And I'm going to give you the correct color for each instance of this game just by circling these lower dots. So here, the correct color was green. And we're going to do this a number of times, and I want to remember, or want you to remember, how many exposures or how many instances, how many bits of evidence were required before you discover the rule. So remember, you just have to choose one of the colors on the screen, and the correct color depends upon the color of the central or the top dot. So here's the first trial. Jochen, would you like to guess a color? What's the correct color?
Didn't we have that one already? Wasn't it green for blue on top, or?
That you're the first person to ever see that. So congratulations. That's yeah. normally people will just guess randomly, and then I'd explain, of course, there's no way that you could at this stage discover the rule. You have to accumulate observations, but you're absolutely right. Yes, you were just told that.
I will behave more randomly from here on.
Right, good. Well, here is your opportunity. What do you think the correct color is here?
I will go for red.
I'm afraid it was green. Have another go. What's the correct color here?
Maybe green again.
Well, that's interesting because, of course, there's only red to choose from, so it has to be red. But
Oh,
you're thinking laterally.
Oh, it has to be one of the three colors. Okay.
Yes, it does. Yeah. So it's the color of the the color of the correct circle. And I didn't actually notice that when these were generated randomly, that this was actually inappropriately easy. Right. Now you've got a bit of evidence. Now take your time. I'm using you deliberately. The whole point of this is that you should be thinking about this and taking your time, and that's going to be very relevant when we revisit this, when we do the in silico experiments. But have another guess at the moment.
So for this one there, well, I'm going to go with blue now.
Huh? Oh, I'm afraid it was green again.
Okay. And maybe the next one, green again.
Oh, that's interesting. Yes, you're absolutely right.
But I must say, I don't see the rule yet.
No, I suspect I'm distracting you by getting you to play the game. I wonder whether anybody in the audience has a hypothesis.
Oh, there are lots of chat messages. I'm starting to realize.
Oh, yeah.
There's a guess of clockwise.
I have a guess.
Karl, can you see the chat?
I can't see the chat. So if somebody wants to, or if you could sort of articulate the hypothesis.
I have a hypothesis.
Yeah.
If top color is blue, correct is the one on the right. Top color is red, correct is the one on the left. Top color is green, either way is correct.
Well, that's remarkable. Congratulations. And yeah, so that's absolutely right. So we could stop playing the game now. That is remarkable. And this has happened on a few occasions, but very rarely that somebody gets it after 5 and possibly even 4 moves. It's remarkable because that's actually impossible to do that. So the whole point of this presentation is to try and work out how you were able to do that. It's also remarkable that I've done this game in front of audiences up to 500 people at places like MIT and Edinburgh University and the like. And they to get it by 5 is very, very rare. So it's usually about 6 or 7 before somebody in a large audience gets it. So it is very impressive that you were able to discern the rule after just 5 observations. And I repeat, that is impossible.
Thank you. I'm very humbled.
Right. So let's forget about the game. Here are all the other exemplars that all conform exactly to that rule. And what we're going to do is come back to that rule. Just for your interest, Rita Hari in Finland actually managed to politicize the rule. So an easy way to remember this: if you're red in England, that means you're slightly left wing, and if you're blue, that usually means you're slightly right wing. It's the opposite in America, but you can start to. If you're green, you're usually in the centre party. So there is a mnemonic which comes along with that particular rule. That was actually chosen randomly. Okay, so what I want to do now is just work through very briefly the underlying account that I want to use to simulate an artifact actually playing that game and look at its behavior in relation to your behavior. And the whole premise here is based upon this notion of self-evidencing, which just means that everything, both updating my beliefs about the world as observed, and also beliefs about what I am going to do next, what I'm going to choose, the decisions I make, are all in the service of optimizing a functional of my beliefs. And that functional is going to be a free energy functional as read in machine learning. So we're going to be wanting to maximize this free energy here. And you may be asking, well, what is this free energy? And it simply scores the value of some observations, some observables that are generated by some hidden or latent states of the world that I can't see directly. And it scores basically the probability or the log probability of some outcomes that are characteristic of me, that I would find very plausible, like I'm warm and rich and happy, that would be surprising states or outcomes that would be surprising to me, like being cold or very poor or unloved. So this is often called an evidence layer bound, and it is an approximation to this very simple notion of value. And by maximizing this quantity here, we can think of this as basically a description of maximizing value or reward, where if we associate the reward with this outcome that is very unsurprising. And from that, we can sort of link and talk to reinforcement learning. If you're in engineering, it'd be optimal control theory. If you're an economist, it would be one statement, a simple statement of expected utility theory. If, on the other hand, you were an information theorist, the negative of this quantity is known as self-information in information theory, also known as surprisal, or more simply surprise. And this formulation, this self-evidencing as an optimization process, simply means that I'm going to try to minimize the surprise of any outcomes. And this can be understood from the point of view of the principle of maximum mutual information, or the Infomax principle, notions of minimum redundancy and maximum efficiency by people like Horace Barlow, and indeed the free energy principle. And I think that's a useful perspective, because the average of your self-information or surprise is in statistics and physics known as entropy, which means that as I'm trying to maximize my free energy here, I'm implicitly trying to minimize the entropy or the dispersion of my encountered observations of the outcomes. And of course, that's the holy grail of much of physics and self-organization to non-equilibria, center stage in synergetics. And if I was a physiologist, it would just be a statement of homeostasis. So trying to keep my sort of essential variables within bounds with a low entropy distribution. And the final perspective is that which a statistician would bring to the table. So this quantity, the probability of some outcomes or some observable data, given a model of those data, me basically, is called a model evidence. So maximizing this quantity is exactly the same as aspiring to maximize the evidence for my models of the sensed world. And from this, we can spin off the Bayesian brain hypothesis, evidence accumulation, and its particular schemes or processes such as predictive coding. So that's the basic premise that we're going to work with. But notice this free energy here just speaks about updating beliefs about the causes of my sensations, namely perception. What I want to do is to talk about the imperatives or the kind of free energy functional that would underwrite our choices, our behaviors, and our actions. So effectively treating action as a process of inference, sometimes referred to as planning as inference, forming beliefs about the most likely thing I'm going to be doing in order to maximize my free energy. And just to illustrate that slightly more intuitively, I'm going to, again, I won't ask anybody this time, so that you can all concentrate. But if I was, I'd ask you to imagine you are an owl and that you're hungry. And then I usually ask the person on the front row, and they say, and I ask them, what are you going to do? And they correctly say, well, I'm going to search for my food. And that, of course, is the right answer. And here's a predator searching for its food here. In that answer, there is a lot of, if you like, implications for the kind of calculus you might want to adopt in order to explain optimal behavior. And what I'm going to do is deliberately draw a bright line or a dialectic between two principles that would underwrite a calculus of control or decision making. Later on, I'm going to bring them back together again, but for the moment, I'm going to deliberately contrast them just to emphasize a key point. So what is that key point? Well, the key point is that searching is motivated by resolving uncertainty about unknowns. And uncertainty is an attribute of a belief about states of the world. So just by introducing the notion that the best thing to do is to search, to explore, you are committing yourself to optimizing behavior as a functional of beliefs about states of the world, as opposed to states of the world. So if you assume that the existence of some value functions of the states of the world that would ensue if I did that u sub t here at the previous time point, then I could, in principle, identify an optimal state action policy by simply choosing the action that maximizes the value function of states, and that would be, I've denoted that by pi policy that is a function of any given state of the world. But we've just said that we need a functional of beliefs about states of the world, denoted here by Q, my posterior beliefs about states of the world. So if you commit to that kind of optimality, then you're looking for a principle that pertains to beliefs, probability distributions over states of the world, not states of the world per se. And furthermore, when you're talking about searching for food, you notice immediately that the order in which I do things matters. So we now are in the game of sequential policy optimization and thinking about a path, a policy as a sequence of ordered moves on the world or actions. And this translates technically into now trying to optimize a path integral. In physics, this would be a time integral of an energy, or known as an action. So what we now have is an expression where the optimum policy maximizes a path integral of this functional here, which we'll see is an expected free energy, where I'm computing that by finding the optimal beliefs about the states of the world by maximizing my free energy here. And the reason I'm writing it down like that is just to demarcate the two principles that you would need to prosecute this kind of approach versus this kind of approach. So here you can generally formulate state action policy optimization in terms of Bellman's optimality principle, leading to all of these things which I'm sure a lot of you will be very familiar with and very skilled and fluent using, things like optimal control theory through to deep reinforcement learning and the like. Whereas if you're on this side of the page, you're talking about variational principles of stationary action, or Hamilton's principle of stationary action. And examples here would include the free energy principle that emphasizes operating on beliefs and belief updating of the kind that underwrites artificial curiosity. And in neurorobotics, you'd be talking about intrinsic motivation, these sort of epistemic drives that underwrite exploration. And so what I want to do is just focus on where this comes from, and in particular, the functional form of this expected free energy functional and how it inherits from the free energy itself. So here's the overall sort of conceptual architecture written in terms of probability distributions or Bayesian beliefs. So we get some outcomes here that are used in order to optimize my beliefs about unobservable, hidden or external states of the world by maximizing my free energy. And then I'm using those beliefs to roll out into the future and evaluate the consequences of a particular policy in terms of the free energy that I would expect. And the story I want to tell here, or the agenda here, is, to my mind, a really lovely relationship between ways of unpacking the free energy and ways then of interpreting this expected free energy in terms of things which we will see are quite familiar. So what I've written here, and please, if you don't like the maths, just ignore the maths. I'm using it iconically just to try and draw certain interpretations of this information theoretic formulation of optimal behavior. So what I've done here is just write out in full this free energy in two ways. This is a way that a statistician would understand good sense making, good modeling. So she would be looking for those kinds of explanations for some observable data that were as accurate as possible, yet minimally complex. So you could always separate or express a log marginal likelihood or a log model evidence in terms of accuracy minus complexity. And the complexity is just the degree to which I have to change my mind in order to provide an accurate account of the data. Technically, it's a KL divergence between the prior and the posterior. Just by swapping around these terms, we get an expression which, if you're in machine learning, you'd recognize as an evidence lower bound, or an elbow. Because this is a KL divergence, it's never going to be less than 0. So this quantity is always going to be less than the negative log evidence, which means that this plays the role of a lower bound on this quantity, the log probability of some outcomes, which we've associated with value. Here, it now just becomes a log marginal likelihood or a log evidence. And the reason I'm drilling down on that is that the functional form of the free energy I expect conditioned upon a policy is retained, which means that I can evaluate or interpret the expected quantities of complexity and accuracy in a particular way. It turns out that the expected complexity becomes a risk, the expected accuracy or inaccuracy becomes ambiguity, and the bound and the evidence become intrinsic and extrinsic value, respectively. So what do I mean by intrinsic and extrinsic value? Well, let's just ignore for the moment my preferences, my log preferences, or my value, and focus on this term here, which is the expected bound. What is this? Well, if I just rearrange these terms, it turns out that this is the expected information gain that I would get if I behaved like this and got those observations. So it's essentially the difference between my beliefs about the states of the world with and without observation that would ensue if I pursued this policy here. And in the visual search literature, this is often referred to as Bayesian surprise. More generally, it's just the mutual information between hidden states, the causes of my sensory consequences or observations, here, conditioned upon a particular policy. So what I'm going to do now is try to get back to the Bellman optimality principle by removing uncertainty of particular kinds from the problem. And the first kind of uncertainty I'm going to remove is the fact that I can't see the hidden states. But if I make an assumption that I can see everything, so there's no ambiguity anymore, so that if I see an observation, I know exactly what caused it, then I can equate the observations and the hidden states, and we're just left with this quantity here, which is another KL divergence. It's between the states that I anticipate or the outcomes under a policy relative to my prior preferences. So this is a ubiquitous objective function in engineering known as KL control. In economics, you might, or you could read it in economics as risk-sensitive control. Now, finally, I'm going to assume that there is no intrinsic value or expected information gain available. I now know everything that I can about this particular setup, experimental paradigm, or environment, so that there there is no more reducible uncertainty. And in that context, I'm now left with just the extrinsic value, which we've just said is the expected log evidence, or the expected value, or the expected utility, if I was an economist. And it is this, of course, that lends itself now to the Bellman optimality principle. But to get there, to repair that dialectic, I've had to eliminate or ignore certain sources of uncertainty that characterize belief structures as opposed to observations and outcomes. So from the point of view of the statistician, what we're basically saying is that if you formulate optimal behavior in this specific way as committing to those policies that will maximize your expected free energy, you are Bayes optimal in two senses. In one sense, you are going to be making the optimal decisions in the spirit of Bayesian decision theory, just by maximizing expected value. But you're also going to be addressing this expected information gain, this Bayesian surprise, this epistemic value or intrinsic value that just is the information I expect to gain if I do this. And of course, this has been long known since the 1950s as the quantity that defines the principle of optimal experimental design and underwrites things like active learning of the kind that people like David McKay have been pursuing, and is used a lot nowadays in machine learning. So active inference is just basically combining Bayes optimality read in two slightly different kinds of ways, complementary perspectives. What I want to do now is just give you a very brief illustration of how these principles can be used in very simple simulations, and then we're going to come back to the game that we played at the beginning and simulate an agent and see if it can, or see if you were close to Bayes optimal. So again, this should not be taken too seriously. Certainly the equations, it's just a sketch of the way that we generally deploy this mechanics in order to simulate behaviors and evince sort of characteristic optimality behaviors. And what we generally use is a Markov decision process, which is very simple. It just says that there are states of the world that generate observable outcomes. So what I'm describing here is a model of the way that I would generate something that can be observed. And I'm going to assume that agents have this model in their head, or they are that model, and they're going to update their beliefs under this model. So this model, I repeat, just generates observations that are contingent upon or depend upon states of the world, and the states of the world evolve over time. And crucially, that evolution, encoded by probability transition matrix B here, depends upon what I'm doing. So I intervene in the world, I act upon the world just by changing the way that the state of the world changes from one moment to the next. And, as we've just seen, this policy depends upon the expected free energy, that in turn depends upon my prior preferences or constraints, negative rewards, if you like, usually encoded in a tensor or a vector C. And yet I can equip this model with some hyperparameters over what we generally use, which are Dirichlet distributions. And that is the model that we're going to use to try and explain different kinds of behavior. I have written the specific equations down here. We don't have to worry about those. Crucially, what we do need to know, though, that once you've written down the functional form of your generative model, you can just go to off-the-shelf software to estimate the optimal beliefs, both about the both about states of the world, which are unknowns, but also about my policies, which are also unknowns. So these are the only things I don't know. These are the random variables, the hidden states, and the policies. And if one goes and looks for, I repeat, off-the-shelf standard schemes, in this instance, variational message passing schemes or fixed iteration, one sees these kinds of updates, which will give me the optimal updates to the expected state of the world under a particular policy in the future and indeed the present, and these expressions for the expected policy that I should be pursuing. This is a precision parameter, or a softmax parameter, which is useful in interpreting things like dopaminergic discharges. And the remarkable thing about this is it looks very much like coarse-grained equations that you might use in or use to understand or simulate neuronal dynamics, or at least the updates implicit in neuronal dynamics. And I've just written out here, perception is basically a softmax operator on linear mixtures of representations, that where you can now associate these tensors with connections in the brain, and these expectations as neuronal activity, and this, say, as a voltage current nonlinear operator. So a degree of biological plausibility that also transcends into optimizing the parameters of your model. Here, the initial states encoded by a D tensor, that has exactly the look and feel of associative or Hebbian plasticity, with associative terms not evident here because we're just dealing with single states, but with the equivalent parameters in the likelihood mappings and those transition probabilities, you get the associative term and some decay term here. And of course, our action selection is just consistent with a classic softmax response rule, where the value now is scored by this expected free energy. So again, as quickly as I can, I just want to illustrate the basic behavior that emerges under this formulation. The simulation setup here is very simple. It's just a two-step maze task. This little mouse can make two moves, and it wants to go and find and sit with its reward on one of the two baited arms at the top of the T-maze. But there's a twist here. We've also given it the opportunity to go to an instructional cue in the lower arm that will tell it whether the reward is on the left or the right. So it's an interesting choice for the little mouse. It can either take a chance and go to one of the two arms, which I should say are absorbing, so it has to stay there once it commits to going to one of the arms, and it can be right on 50% of the occasions, and thereby rendering the expected utility or the expected value the same as using the first move to go and get the instructional cue, and then with a degree of confidence going to find and secure its bait here. Both instances have the same expected utility or value or extrinsic value, but of course, from the point of view of the expected free energy, going to resolve one's uncertainty by going to the instructional cue is the preferred option. It's the most likely thing that I'm going to be doing as a curious creature, or in this instance, a curious mouse. This is the generative model for this system in terms of the probability transitions and the likelihood mapping. It's really, really simple, and it just takes seconds to build and to solve or iterate to produce behavior. And this is the kind of behavior that ensues. What we've done here show the results of 32 trials, scored in terms of where the reward is on the left or the right, and in terms of the posterior beliefs about what policy is the mouse going to pursue. And here we've equipped it with 12, or in fact 11 policies, so it can stay where it is and move down here, or it can go over there and then go over here, or it can go down there and then go over to the left arm. So different combinations of policies that have two steps in them, each scored by the expected free energy, and then it will commit to or sample from the action from the policy that is the most plausible or likely. And here are the performances. This is the learning of the initial conditions. Basically, the context is the reward on the left or the right. So what happens? Well, as one might imagine, initially, this mouse, synthetic mouse, responds to the epistemic affordance offered by the instructional cue, or say a condition stimulus, and then goes to, having found out where the reward is, goes and sits with the reward. And this behavior persists for many, many trials. But in this example, we played a trick on the mouse by leaving the reward on the same side all the time. And what this means is that as the animal or the mouse explores its environment, it starts to realize that the reward is always on the same side. So that the epistemic affordance, or the intrinsic value of the policy that involves going and querying the instructional queue, gets smaller and smaller and smaller, until at some point it goes below the expected cost, negative cost, or the expected value afforded by going straight to the reward. And so at trial 20, there's a deterministic switch from explorative behavior to exploitative behavior, where the mouse goes straight to the reward. And this is just a consequence of resolving uncertainty about the environment, learning about the environment, reducing the contribution of the expected information gain to the expected free energy, thereby revealing more exploitative behavior that has this pragmatic aspect and more goal-seeking as opposed to information-seeking aspect, as the as the mouse learns that this the instructional queue no longer has the epistemic affordance it once had. You can do all sorts of things with these these simulations. You can get in under the hood in terms of the dynamics that underwrite this variational message passing and fixed point iteration scheme, sometimes called coordinate descent, and you can sort of simulate electrophysiological studies here illustrated in terms of looking at the neuronal representations of the chosen versus the unchosen option and how they evolve during the particular trial. You can sort of plot the activities as a function of where the mouse is and demonstrate things that look very similar to place fields in the hippocampus, and do all sorts of things like mismatch negativities and the like. But what I want to do is to close, though, with a reconsideration and revisiting of the task that we engaged in at the beginning. When simulating an agent trying to discover this rule, one has to sort of get right into the details in terms of everything that the agent has to do. So in this instance, you have to write into the GeoGebra model the opportunity to go and look at each of the colored circles and then make a decision by declaring the choice, in this instance by, first of all, foraging for information, exploring, and when making a decision, then moving from an undecided to a I've decided. I think it's in this instance the green is the correct color. So to see whether this agent can discover this rule, we have to write down a generative model. It may sound complicated. It's not actually, in the sense that all you need to do is to just write down all the states of the world that will be necessary to generate all the outcomes. And all the outcomes that we need to generate are: what is the color of the circle that I'm currently looking at? Where am I currently looking? And have I received any feedback, right versus wrong, at this point? And to generate that, I just need to know what is the rule, is the correct color on the left, in the center, or the right? What is the color? What is the color in question? Where am I looking? And have I yet chosen? And with these factors of hidden states, I can sort of generate outcomes of any given combination and write that down as a tensor that I've unpacked here. It's a likelihood mapping that's sort of high dimensional. Again, we don't need to worry about the details, but just for interest, the characteristic form of these likelihood mappings is such that interesting contingencies and lawful contingencies or rules that govern outcomes of the kind that you were trying to discern are usually expressed in terms of very structured, sparse mapping. So, for example, here, there is a direct relationship between the color I'm observing and the correct color that depends upon me looking at the left circle and the rule being left. So I just write that down as a lawful relationship in this likelihood mapping that is very context specific to this particular combination of factors. Another example here, if the rule is left, then it must be, if I'm looking in the center, I must be seeing a red. If you remember, red is left wing in England. And similarly for the other colors. So I can write down everything that that would encompass that rule, the structure of this particular lived or sensed world in this likelihood mapping. To actually simulate an agent that has to discover that rule, I basically just equip it with what you knew, which is the rule depends upon the color of the central circle, so the color that I would see if I was looking at the center, but you know nothing else. Everything else is uninformative with no information. And your job now is to use your experience to accumulate knowledge, to learn the likelihood mapping, and then discover this structure, at which point you should be able to respond correctly by predicting the correct color without actually seeing the answer. So that's what I'm going to simulate using exactly that message passing previously illustrated to ask, well, how many trials? Well, first of all, let's just look at the results. So what we've done here is play the same 32 games that you saw in at the beginning of the presentation. And again, using the same format to describe the planning in terms of posterior beliefs about the policies I should be pursuing, or where should I look next, or do I go and declare this is the correct color? This is the initial state, the center, the color of the center Q. These are the final outcomes and performances, and this is the free energy and the associated confidence. Unfortunately, this is a negative free energy in this graphic here. But what I wanted to show is, in terms of performance, the reds are mistakes. This is where the agent got it wrong. And one can see that after about 14 trials, the agent makes no more mistakes. And furthermore, she's pretty confident about her response, about the hidden states of the world, and also her beliefs about her policies, what she's going to do. And this isn't accompanied by a reduction in negative free energy or an increase in her sort of proxy for this marginal likelihood or model evidence. So one could say that this synthetic agent has learned this rule by about 15 exposures, as evinced by her behavior. And indeed, one can do all sorts of interesting post hoc analyses on the belief updating. One interesting one is that, could one anticipate certain differences in belief updating and the simulated neuronal responses before and after understanding the nature of the contingencies that are producing the outcomes? And we can do that just by choosing two trials with exactly the same stimuli and exactly the same behaviors, but before and after learning. And when we do that, we can sort of illustrate this belief updating using things that look a little bit like firing rate rasters or synthetic local field potentials that inherit from the belief updating, where we're assuming that neural activity is encoding these expectations. And what I wanted to draw your attention to is the interesting phenomena that when this agent starts to understand what's going on, then the stimuli acquire a very specific meaning. They have information that has a meaning in relation to the agent's understanding of the world. And you start to get these, despite the stimuli being exactly the same in both of these instances, you start to get simulated evoked responses much earlier in the trial, as the agent is actively sensing or soliciting information to build her beliefs about what she is going to do next. So that is interesting, but it sort of overlooks a key question. Why are we looking anywhere if the consequences of action had no meaning and could resolve no uncertainty at the beginning of the trial? And this is a subtle thing which takes us to the next level I wanted to talk about, which is the expected information gain, not in terms of epistemic affordances that resolve uncertainty about states of the world, but about the knowledge about the world that is entailed by the parameters of your generative model. So you can play exactly the same mathematical game by also applying this notion of expected free energy, not to the states of the world, but to the unknown parameters that structure my generative model. And in this instance, that expected information gain, that intrinsic value, looks very much like novelty. And it is that which was driving this epistemic foraging prior to learning the rule. So put that another way, we can sort of decompose this expected free energy into expected information gain about parameters, namely novelty. And if you want a word for the expected information gain about states associated with a particular policy, we often refer to that as salience to distinguish it between novelty and then our utility at the end in the usual way. Put simply, what this means is there is an epistemic allure to discovering what would happen if I do that. So it's not the state of the world, it's not what is behind that door, it's can I open that door? It's something that is about the structure of the world. And that brings me now to the final point, which brings us back to your remarkable performance at the beginning. So this Bayes optimal agent, equipped with all the equipment of optimal Bayesian design and expected information gain, you deployed on exactly the evidence and the game that you were exposed to. Took 15 trials before one could say it learned the rule. There was no hint really of a sort of insight or the kind of, aha, that's the rule that you actually did. So normally, as I say, audiences normally take sort of 7 to 8 moves or exposures. I should have moved this down to 5. You actually got it here, which is absolutely remarkable. Why? So how on earth did you do this when I've just shown you Bayes' optimal behavior requires 15 moves? Does anybody have any ideas?
I can tell you why I did.
Lovely.
Because I trusted myself. So I basically thought I got it right. And that was enough for me.
So you had high confidence very, very early on.
Yes, but that...
What gave you that high confidence?
I think I was expecting an instinct to contradict what I thought the rule was. And when I didn't see it, I thought, okay, that's it.
Excellent. So you used abductive reasoning with a little bit of hypothesis testing based upon the evidence at hand. And the way that you phrase that, I think, has exactly the answer I was hoping to elicit, because you talked about the notion of a rule. So you had a rule you knew that there was a rule. You didn't know what the rule was, but you knew there was a rule. And therefore you were looking for evidence for your particular hypothesis or rule, and you didn't find any contradictory evidence and felt confident that you could commit to that rule to the extent that you switched off your microphone and articulated it. So the fundamental difference between your kind of Bayes optimality and the kind of Bayes optimality that the agent thus far has expressed is the fact that you knew there was a rule. You knew there was a space of these likelihood mappings that were that existed, that was rule-like. And that's what I'm going to now try and do in terms of bringing the third level of optimization to the table, which is the structure learning. And it's an interesting one because, so here's this sort of extended architecture where now we're contextualizing active inference, sense making, and planning as inference, now underneath or unfolding in the context of exactly the same kind of optimization processes that inherit from learning. I just want to focus on the things that go into the learning in terms of optimizing this free energy associated with the parameters per se, and just make the point that learning is all about updating my parameters, the weights in, say, a neural network. But we're also in a position to update our priors in a way that will optimize the free energy by moving our priors closer to our posteriors. But if we have to do that, then we have to choose certain sets of prior beliefs in order to score the improvement in my free energy or my model evidence afforded by testing out that hypothesis or that particular rule, where the hypothesis or rule is just written into the structure of, in this instance, my likelihood mapping. So I could, in fact, I probably do, and probably you did, have in mind a whole bunch of different rules. You could articulate, obviously these agents don't articulate them, but they can certainly have them in mind in the sense that they can try out a whole series of hypotheses that are rule-like, simply in virtue of the fact that they have structure. They have contingencies that are context sensitive, just by populating these parts of these slices of these tensors with sort of identity matrices here. And there are about 64 of these rules, and I can go through them and assess their appropriateness by rehearsing what I've seen so far under each of these models or structures. And then I can weight each of these structures by their likelihood as scored by the free energy or the marginal likelihood. And I can, just by knowing there's a rule, I can now do structure learning and accelerate the efficiency with which I make sense of my observations. And one take on this is implicit in this argument that we can optimize our priors to minimize the complexity. But notice this process has got nothing to do with accuracy. So we can do this kind of complexity minimization, this kind of pruning, this housekeeping, in the absence of any observation that subtend the accuracy here. So the idea here is that this kind of structure learning that pertains to the parameters is a kind of thing that we do when we're not actually gathering information, either when we're introspecting or closing our eyes and thinking about things, or indeed when we're asleep. So the idea here is that we accumulate lots and lots of, in this instance, Dirichlet parameters of a likelihood mapping that encode the mapping from the rules that move from cause to consequence. And we accumulate all of these associations, if you like, during the day, for example. And then I've got an overly complex model, which I'm then going to prune using a process that we refer to as Bayesian model reduction, that maximizes the evidence, but does so by minimizing the complexity, to prune away all those redundant associations, to get back to the simplest structure that maximizes the or improves the model evidence in relation to the model structure itself. So I've cartooned that as a distinction between parametric learning during the day using associative plasticity, and then in accord with things like Julia Tononi's synaptic homeostasis hypothesis, a complexity minimizing structure learning that you can regard as biologically as this kind of synaptic regression. And that, for some people, is the raison d'etre for sleep. So when we implement this Bayesian model reduction, this kind of structure learning in the model, we now get much closer to the performance that we witnessed earlier on from our human audience. So here are the prior beliefs of the structure of the world as entailed by this likelihood mapping as we start the process. And here are the true structure. And here is the learned structure after 12 exposures. And here's exactly the same structure, but I, in this instance, intervened between every exposure with a little time of reflection to do the Bayesian model reduction, which is why I was saying I'm distracting you. You didn't have a chance to do your Bayesian model reduction, whereas the rest of the audience did, and showing that you can arrive at this free energy minima much more quickly, or with the same, with a shorter number of exposures relative to an agent that did not have this capacity to explore different rules. And this, I think, is one of the final slides now. It just shows a comparison of the behavior with and without this kind of structure learning. So the average performance with is much better, averaged over 64 instances, different trials. The first one was formally identical to the one that you played, but I'm averaging now over multiple trials. And I'm showing the point at which there was a commitment to a categorical change, a selection of a new prior structure. So this now has a saltatory, it's an event where I'm choosing this hypothesis on this model over that model, which is much more like this sort of aha moment that a few of you may have experienced, and certainly after you saw the rule, you would have experienced it. So the blue, purple, sorry, magenta circles are when agents first were able to discover the rule using this kind of structure learning. And on average, over different trials, they did actually attain your performance of 5 exposures. Interestingly, though, it even took this agent equipped with Bayesian model reduction or structure learning about 8 moves before it actually solved the particular problem that you had to solve. So you're still outperforming Bayes optimality in this particular instance. So in conclusion, I've been talking about, I guess, developing minds, or at least brains, at 3 different levels in terms of resolving uncertainty about the lived world. Uncertainty about states of the world, about contingencies, laws, and about the structure of the generative model in and of itself. And I'm associating that with planning and inference in terms of uncertainty, where the epistemic affordances of expected information gains can be read as salience, uncertainty about contingencies and associations as parametric learning, where the epistemic affordance can be read as novelty, and uncertainty about the model itself, I discussed in terms of structure learning. I've never written this down, but I guess one could look at that in terms of aspiring to knowing one's world, and emphasizing the great importance of not only having lunch, but also going to sleep properly. And all this rests upon complexity minimization. So I'm going to close with a quote from Einstein, this emphasizing the importance of negative complexity or simplicity. Everything should be made as simple as possible, but not simpler. So it just remains for me to thank those people whose ideas I've been talking about. And of course, thank you for your attention. Thank you very much indeed.